অ্যাকচুয়ালি দুজন কালকে আমার কথা আছে, একজন অ্যাবসেন্ট আছে, মেবি ইনিও অ্যাবসেন্ট আছে, দেখছি না, এটাই লাস্ট টক আজকে। সেমিস্টার The title of my presentation is Electrochemical Staff and Theme of Opinion and Replying to Students' Research. The focus of our research is to model compact star, more specifically strange star in the modified gravity theory. So why modified gravity? Despite its success, GR can face challenges accommodating dark energy, dark matter, return isolation, crystals, astronomy, etc. So that's why we turn to modified gravity theories like F2 gravity, where geometry is described by non-metricity rather than curvature like in GR. So this provides a minimal deviation from GR while preserving second order equation, thus avoiding the higher gravity pathology that arises. So the main goal of our research work is to construct a singularly stable stellar model in a linear F-cube gravity. In this work, we have incorporated anisotropy because at very extremely dense compact objects, which is around the density is around this 15 gram per cc, the matter is highly non-isotropic. We have modeled these stars as stage stars, which is composed of stage quark matter, and this is modeled via the MIT Background equation of stage. So these are mathematical setup. The action term is given by this integral by Q is the non-metricity here. We have specifically adopted a linear form of F2 gravity where alpha is the coupling parameter and Q is the non-metricity and phi 0 is an arbitrary constant. For alpha equals to 1 and phi 0 equals to 0, this reduces to a Q equals to Q, which is the symmetric territorial equivalent of GR. Describe the star, we have assumed a static spherical symmetric light element given by this equation where mu and lambda is unknown metric potential. This unknown metric potential defines the geometry of the interior of the star. With the help of this, we can directly fill equation for this for the linear F2 gravity. We can see that here we can link the physical quantities like the energy density, the radial pressure, and transfer pressure to the geometry of the star. We have assumed one of the unknown metric potential given by the physical gravity where the mu is the static parameter. We have the matter composition is described by the MIT Background equation of state, but you can see that this establishes the relation between the radial pressure and the energy density, and Pg is the exact constant. We have now to solve for the another unknown metric component. We employ the Zuckerberg energy transformation. So the differential equation are much easier to solve. Now that we have the interior metric, we now have to find out the external metric. For this, we have applied this condition, and with this help of this, we find out that the sculpture de-Sitter line element comes out naturally from the F cube to the linear gravity. Here we can see from this metric we can physically describe the importance of the phi 0, and it can be termed as the effective cosmological constant. Now we match the exterior metric and interior metric at the boundary of the star and the r is the radius of the star. Radius of the star. These are the boundary conditions. Additionally, assume that the radial pressure was vanished at the surface. With these three boundary conditions, we can find out the unknown metric, the unknown parameters of that present in the model. Now that we have everything about the model, before analyzing the model, we need to establish what makes a realistic. So it has to follow some certain criteria. The regularity condition states that the energy density and the radial and the pressure profile must be finite and positive inside the star. The model must maintain isotropy at the center of the star. The causality condition must be met inside the star, which states that the sound speed inside the star must be less than 1. Yeah, 1 represents the speed of light. The average index must be greater than the critical value, which we will talk about later. The energy conditions, the weak, strong, and dominant energy condition must be satisfied. So to analyze this, we consider this non-compact object with mass 1.7 kilograms and radius 9 kilometer. With the help of this, we get this equation from the model, and with a stable range of the black parameter, we can map this against the alpha, which is the complete parameter, and mu is the parameter. And from here we can see that for mu greater than 5, which is also a constant, for 5 we can set a limit for the alpha, which is still between 0.6 and 1.5. Now for the rest of the project we choose a value between this, which is 0.85. This is still in a constant or Riemann relation. Now this plot shows the gray area here shows that the observational limit or different pulses that are taken from neither observation. Now, for any model to be in a wire, the MR plot, which is the mass radius relationship, must pass through this gray area. Now, for our model, we can see that for mu equals to mu greater than equals to 7, the MR profile passes through this gray area. And you can see for different values of for as the mu increase, we can see the mass radius profile here. So this sets a strict lower limit for the sphericity parameter. Here the density pressure and aspect loss, we can see that the energy density, the radial pressure and the transfer pressure are all positive and finite throughout the star. The anisotropy, which is the difference between tangential pressure and radial pressure, is plotted here, and you can see that it vanishes at the center, which maintains isotropy. The stability is analyzed through sound speed and adiabatic index. Here in this plot, you can see that the dotted line is the square of the radial sound speed, which is 1/3, and the square of the tangential sound speed, which is this solid line, and for different values of mu, and it is within the limit less than 1. So the quadratic condition is satisfied. The critical value of the adiabatic index can be found out from this equation, where m and r are the mass and the radius of the compact object we have considered. So you can see from this plot that all the solid lines here indicate that for different values of mu, the adiabatic index is greater than this dashed line, which is the critical limit. So adiabatic index is also greater than the critical limit. Here are all these energy conditions. So which must be satisfied. So we can see from this plot that all the energy conditions are satisfied and within the limit. This tells in modified UV equation, which tells the Heisler equilibrium. So we have 4 force gradient, but for linear form of FQ gravity, the fourth gradient, which the FQ term vanishes because the FQ term vanishes, and we are left out with 3 terms only. Here you can see the Fg, which is the gravitational, the attractive gravitational force, is balanced out by the hydrostatic force gradient Fh. And the anisotropic force gradient, you can see that towards the center it is negative, which means attractive, but towards the surface it is repulsive. But it is necessary that the summation of all these 3 forces must be 0. So you can see that this dashed line is the summation of all the 3 forces here vanishes. So the hydrostatic equilibrium is found. So to conclude the talk, so we have constructed the synergistic model in the linear gravity. We obtained this structured X-ray solution naturally from the theory. The MIT back model and the variable limit of the back constant set a limit for the constant of the on the coupling parameter. For the mass radius equation, we can set a strict lower limit for the sphericity parameter. Now we have applied this methodology to some different compact objects with different mass and radius, and we note that all the stars are identifiable with this stellar number. I would like to thank my guide, Professor Vikas Chandra, for his support. Thank you.
So, what is the exterior space-time that you have used?
So the exterior space-time I have obtained it from using this condition here, which is this version, this is the line.
Why so? Why not simply version?
So this exterior alignment is not just considered. We have found it from this equation, from the field equation. Now this is the field equation. So this is the
No, I understand that. Go back to that side. Yeah, so that cosmology constant, what value you have chosen for phi naught?
It is around 10 to the power 35 around this value.
What is the cosmology? Value of the cosmology constant?
So I don't recall the exact value, but it is of the same order.
Which order? What's the number?
10 to the 35.
It's much smaller. 10 to the minus 52.
Oh.
Can you imagine? So that makes alpha naught.
So I might be
Alpha
might
naught.
not recall it
Alpha
properly.
naught. Your phi naught is essentially zero then, right?
Uh, no, sir, but we can. It might still
So,
this year, but for the model we
so,
can.
see, this metric will be interesting in the context of cosmological scale, but for a localized body, phi will be phi naught will be more or less equal to zero. Now go back to your postulate where you have assumed the form of the modification, F2 modification. I think you have written somewhere that phi naught is essentially zero, right?
Right.
So essentially, it's like a linear combination of it's a linear of that electricity factor Q varies with alpha. Now then again there is a problem. Problem is that again you say that when it's alpha equal to 1, you get back the Einstein theory, right? Yeah. But even if you take other values, you also get a slight scaling of the GR results. No new physics will be available. So for that you need to choose something different, like nonlinear
So
modification.
nonlinear form of electrogravity might introduce some
But that's the only way that can give you giving set. Otherwise, you will get simply the rescaled version of GLSS. So,
right, sir, but
yeah.
the nonlinear form, there's some papers that say that nonlinear form might not be right.
No. That's the only way you can do it. I mean, you can choose. I mean, there are many papers available. I mean, so this is well understood that okay, I mean that for whatever value that you choose for alpha, that is simply rescaling of the GLSS. Okay, so that is not typical modification. For one modification, you need to have like q to the power alpha, beta, whatever n. So that's one thing. And secondly, it's not required at all. So far as this exterior system is concerned, it's essentially Schwarzschild. Because that cosmological constant for this localized object is more than zero. And that is expected. I mean everywhere you will find that the exterior of a localized body is Schwarzschild, not Schwarzschild.
No. Okay.